We're just going to get right into it. We're going to be doing chapter 5, and there are two problems which are kind of difficult to explain, so that's going to be in a separate video. But for now, we're just going to be doing like 20 out of 22 questions, which I think is pretty substantial, right? Alright, so let's just get into it. For question 1, we're asked to find which one is the achiral molecule. Alright, well, if something is achiral, it just means that the carbon is going to have two of the same groups together, usually, right? So, for instance, this carbon right here, right there, that would be classified as achiral. Why is it achiral? Well, notice that you have a bromine attached to that carbon, and you have another bromine attached to that carbon. Because you have two of the same groups, the group being bromine, because you have two bromines attached to the same carbon, that carbon right there is achiral, not chiral. Okay, so this carbon right here is achiral. Okay, well, what about the guy in front of him? What about the upper carbon? Well, this carbon has a bromine, a chlorine, a hydrogen, and it has a carbon that has, it's different. So this carbon right here is completely different from the top one. And because this carbon is different from the top one, you could say that it's chiral. So for instance, to really to clarify what I mean, I'm just saying that this whole group right here, you can think of it as being attached to carbon. And so that whole group is different from this whole group, right? This whole group has two bromines, and this whole group only has one bromine. And so that is different. And because carbon has 4 different groups, that's going to be called chiral. It's going to be called chiral. It's important for you to know that if you have a molecule that has 2 stereocenters, which just means chiral center, or a stereocenter. If you have a molecule that has 2 stereocenters, and one stereocenter is chiral, and the other one is achiral, well, you're always going to be chiral, right? And so as long as you have one chiral, you're always chiral. Chiral. Okay. So, yeah, this one is achiral, but overall, right, you're still going to be chiral. So, that's just for in the case of if you have 2 possible stereocenters. If you had chiral, then for sure you're going to be chiral, right? If you have chiral, achiral, it's still chiral. If you have achiral and achiral, then that is overall achiral, right? So as long as you have one chiral center, you're always going to be chiral. And because we're looking for achiral, this is not the correct answer. So this is wrong. 3 is wrong. Because as long as you have one chiral center, you're going to be chiral. So number 3 is wrong. All right. What about 2 and 1? All right. Well, we're looking for achiral, right? All right. Well, let's see. We have a hydrogen, a bromine, a chlorine, and then this big guy. So that's different. That's going to be chiral. Let's just put a C. What about here? 1, 2, and 3, and then this other guy. That's another chiral carbon. And so, for sure, because you have a chiral and a chiral, right? That's going to be what? Chiral. So that's bad because we're looking for achiral. And I just proved to you that this overall is a chiral molecule, right? It's a chiral molecule. And so number 2 is also bad, right? So it cannot be D because, more of these choices are bad. But what about this one? Well, you're probably saying, Brian, this one's chiral for sure. There's a chlorine, a bromine, a hydrogen, a bromine right there, chlorine, and a hydrogen. And so technically this is chiral. you're saying to me. And I'm like, yeah, for sure, that is chiral. But you're failing to consider symmetry. Well, what do you mean, like, symmetry? I don't see symmetry. I get it. I understand. So here's a trick that you can do. For instance, so you see how we have this, right? Well, you can do what I call the triangular method. It's a method that I made up. It simplifies everything. So, you know, hopefully I get famous off of this method, kind of like Fischer did, or Newman. And so, let's just do it. Okay. So, you know, this is trademarked, by the way. So, the triangular method means that we're going to make a triangle, right? You see that triangle? Okay. All we have to do is put this bromine over here, this chlorine over there, and this hydrogen over there. And so technically we made a triangle. Here's my triangle. My bromine is going to be in chlorine right here. Okay, and that chlorine is going to go to the hydrogen. And my hydrogen is going to go to the bromine place. Oop, sorry. Okay, and there we go. Right. So, oh, I'm sorry. So it's different ways to do it. I'm really sorry. I should have looked what I was doing. So instead, we're gonna put bromine over here. These are like super bad. Sorry about that. But hey, that's a learning moment, I guess. So yeah, you could go that way, but that's not really beneficial. Usually you just want to go to like base to base. So like bromine goes to hydrogen, right? And then hydrogen goes to this guy right there. And then chlorine goes over there. Okay? So like I was saying, I didn't mess up, you know, I totally did that on purpose. So bromine is going over here. My hydrogen is going to go over there. And my chlorine, my chlorine is going to go over here. So what did I do? Well, I did the triangular method. So, you know, you could do, so to make it official, you could do, you know, Brian's triangular method. Okay, the method, right? And you know, that's totally trademarked. So all I did was I put my bromine to hydrogen. So we went here, right? So bromine to hydrogen, and here's chlorine. After that, my hydrogen is going to go here, and then my chlorine is going to go over here. And it's kind of like a cycle, right? So because bromine went to the right, hydrogen is not going to be able to go to the left because that's oncoming traffic. And that's pretty dangerous for little hydrogen. So he's going to go downwards. He's going to go to chlorine, and chlorine is going to go upwards to bromine. And as you can see, when we do the triangular method, that you actually get a plane of symmetry. Right there. So if you were to fold this in half, you would have hydrogen on hydrogen, chlorine on chlorine, bromine on bromine. And because that's a symmetrical molecule, we can classify that as a Miso molecule. Miso. And by the way, whenever you want to do the triangular method, just go from left to right. Right? So from Br to H, you always want to do the method like that. So this is a Miso molecule, and Miso molecules, well, they turn chiral to achiral. So first you have to be chiral. First, be chiral. And then after that, you have to have a plane of symmetry. Must have symmetry. Right? And so we are chiral initially. We have symmetry now because we did the triangular method. And because we're chiral and have symmetry, we're going to be Miso. And Miso makes it asymmetrical. I mean, not asymmetrical, but achiral. So because we are meso, we are achiral, and we're looking for achiral, and so we're going to say that this is good for us, right? So that's pretty good. A is correct answer. Okay. Now number 2, which of the following compounds are chiral? Now, I'm not sure, if he wanted pairs or like if only one answer choice is correct or not, because he didn't give us an answer key for this one. But I would say that all of them are chiral. Why is that? Well, I want to address this guy first. I want to address him first. So if you can't make the jump between a Cherenkov formation and the actual cyclohexane, I'll show you. So you see how this is upwards, yeah? This is up, and this is upwards. This is downwards. You see that? Well, if we do a cyclohexane, this guy right there, the tip right there, is this person. Okay, so we're gonna be over here when we're talking about this. Okay, so this is upwards. Whenever you see something upwards on the cyclohexane chair, it's actually just a wedge. So that's a methyl group as a wedge. And we're just gonna put our implied hydrogens on the hash. Now, we're gonna go here, which is there. So there's nothing there. We have over here is there, which is nothing there, right? And though this guy right here is this person. Okay. So we're going downwards. Well, when something's down on a chair, it's gonna be a dash. Sorry, a dash. So that's a methyl group as a dash, and then we have our implied hydrogen on a wedge. Okay. So you can see the problem here, right? I hope you can see the problem. So for instance, for cyclohexane or for cyclomolecules, this would be pretty good. You have a wedge. Those are the same things. You can make a plane of symmetry and then fold them together, and that's good. It also works for hash, right? The dashes. But when we have dash hash, that's not good, right? And so, you can't compare a hash and a wedge. Those are completely different, right? And when you're doing symmetry, you're expecting the piece of paper to be equivalent. They're going to have the same face on each side. But is a wedge similar to a dash? No, they're completely different. And so symmetry is all thrown off. And so I'm saying here, is a wedge hydrogen the same as a wedge methyl? No. So there's no way for this to be symmetrical, right? And if it's not symmetrical, then most likely it's going to be chiral. And so we look at a chiral carbon right here, and we're like, yeah, for sure, that's chiral. There's a methyl, a hydrogen, a CH2, and then this guy right there, that's completely different when you're talking about chirality. And so I would say for sure this is chiral. And over here, it's the same thing, right? You have a wedge and a hash. So is a wedge methyl the same as a hash methyl? No, they're different. And so these are not Miso compounds. They do not have a plane of symmetry. Okay? So that would be chiral for sure. Over here, if you were to do a plane of symmetry, you see the problem. You would have something like this. If you were to fold this on a piece of paper, you would have and let's kind of like do like a juxtaposition, right? If you're an artist. So this wedge right here would go to this blue, not a wedge, but this blue pink methyl would fold into the blue methyl, and that's cool. But now this group would fold and kind of be like adjacent to this methyl or to this double bond. And so that's not very good, right? Like, if you are more of a tactile person, you could just write it out on a piece of paper and try to fold it, or like on a napkin or something. And you're going to see that, these double bonds kind of mess us up in symmetry. And because we don't have symmetry, I can say that most likely is going to be chiral. Maybe. Right? So I know for sure 2 is chiral, and 3 has to be chiral as well. And 1 is kind of a toss-up because he didn't give us hashes or wedges, and so that's kind of iffy. Right. Moving on, we have to find the pair of enantiomers. So whenever we're doing enantiomers, you're really just looking for, if something's S, then the other pair has to be R. So one molecule is S, the other one is R. That's going to be enantiomer, or it could be R and S. Or if you're dealing with a molecule with 2 chiral carbons, you're going to have something like RR, and then you're going to have SS. So this whole molecule changed. So RR versus SS, that's going to be enantiomer. Or it could be SS versus RR, right? That's enantiomers. Well, to be an enantiomer in the first place, you have to be chiral. So enant, that equals chiral. Okay, so to eliminate some of the answer choices really quickly, you just have to look for something that's not chiral, right? Because if you're not chiral, you're not an enantiomer. So let's try to pick off something that's not chiral. This carbon right here has a hydrogen and another hydrogen. And so it has 2 of the same groups. That's going to be achiral. Let's call that AC. All right. So 5 is wrong. 5 is wrong, so that's bad. Okay. Do we have anything else? Let's see. Okay. So we have a CH3 and a CH3. And so that is also achiral. That carbon has 2 of the same groups. In this case, it has 2 methyl groups. So that's bad. Anything with 2 is bad. Okay, so that's a 2, I hope. And that's a 2, I hope. And so, hey, we eliminated answer choice A, B, and D. That's pretty nifty, right? Cool. All right. Now we have to figure out the pairs. So I know it's going to be 3 and 4, most likely. Well, let's try to figure out what's 1. Okay. So, it's the first few problems, and I just kind of want to like go really slow on these first few problems, and then kind of like breeze through the other questions. So it's kind of like get your first taste of stereochemistry. All right. So whenever you're doing stereochemistry, you have to follow these priorities. And first, I want to do atomic number. After I do atomic number, I want to do carbon heteroatoms. And what's a carbon heteroatom? Well, a carbon heteroatom is a carbon that is attached to literally anything else other than hydrogen or carbon. Right. And now, after that, so this is priority number 1, this is priority number 2, and then priority number 3 is going to be that you're going to prefer, you're going to have a higher priority for a carbon that's alone versus a carbon with a hydrogen versus a carbon with 2 hydrogens versus a carbon with 3 hydrogens. So a carbon that has 4 bonds is better than a carbon that has a hydrogen, and that's better than a carbon that has 2 hydrogens, and that's better than a carbon that has 3 hydrogens. Okay, so that's very good. Let's actually prioritize now. Okay, so this is actually chiral. We can agree on that. So what am I going to prefer? As a chlorine, a carbon, or a hydrogen? Well, I'd rather prefer, not a hydrogen, but a carbon. So I'd rather prefer the chlorine, because the chlorine has an atomic number of 17. So that's priority number 1. Well, now I'm just comparing carbons. So what am I going to prefer? Right? Well, I'm very silly, sorry. Number 1 is incorrect because, I'm sorry, that's a methyl group and that's a methyl group, and so they share the same base or the same group. So that's achiral. I apologize. So it has to be like 3 and 4, right? But let's prove it. So this is priority number 1. Which am I going to prefer? Carbon H2 or carbon H3? Well, you know, I'd rather have the carbon H2, right? It has less hydrogens. I don't care about all this. I'm just going down the line. Going down the line right there, right? So it's going to be 2, 3, and 4. Hydrogen is in the back, right? So we can go, let's do it in blue. We can go 1, 2, 3, and that's what? An R. That's an R shape. R shape. So this is R. Alright. Well, notice something. This hydrogen, which is going to be my lowest priority group, it has an atomic number of 1, which is bad. This hydrogen is not in a hash or wedge, and that's pretty bad. What can we do to prioritize? Well, whenever your lowest priority group, because sometimes hydrogen is not your lowest priority group, sometimes you don't have hydrogen, sometimes you have like fluorine, right? Let's say that fluorine is your lowest priority group. Well, you're going to have to put your lowest priority group in the back. And so for this one, I'm going to rewrite it, but instead, I'm going to put my lowest priority group in the dashes. So I will have H3, and then we're going to have like a bow tie or something. Okay. And now I'm going to put my hydrogen in the back. And whatever was in the back goes in the position of the hydrogen. And we're just going to say it's CH2 because I'm lazy. And chlorine didn't move. Okay. So now we prioritize as normal. We have 1, 2, 3, and 4. I'd rather have a CH2 than a CH3. So that goes 1, 2, 3, right? And let's see here. 1, 2, and 3. That's going to be R. Alright? It's going to be R. Right there. However, you want to reverse what you did because ultimately you did move that hydrogen. And so you want to reverse what you did. So instead of having R right there, we are instead going to have a what? We're going to have an S. So I have an R and S, so that becomes an enantiomer. So that's RS enantiomer. That's C, 3 and 4. So I know it's a little weird. You can think of like, well, it's just weird, right? So for a recap, just put your lowest priority group that's not on a wedge or hash, put it on a hash, and put the hash on the line. And so we will have 1, 2, 3. Oh, that's R. Well, yeah, but you're going to have to reverse what you did because you moved the hydrogen. And so truly, you have an S. So, you know, you can replay that as many times as you want, but it's, you know, what you have. And I recommend that you watch this the 2-hour stereochemistry practice video to really get accustomed to stereochemistry. Not fun. We have to find what is R2-chlorobutane. Well, if we're looking for R, then for sure we have to be chiral. So I'm going to be looking first for whatever is not chiral. So H and H, that is not chiral, so it cannot be 5. Let's go over here, let's see. So, yeah, this is all we have. We have 1 through 4, sorry. And over here, we have a CH3 and a CH3, so that is not good either. Do we have anything else? Let's see. Methyl, hydrogen, chlorine, CH2, what's that? Okay, so, oh, and over here, we have a methyl group and a methyl group. So for sure, always double check. So it's either 3 or 4. We have to figure out which one is an R. So priority, remember atomic number, that's going to be number 1. CH2 is better than a CH3, so that's going to be 2, 3, and 4. Hydrogen is in the back. That's our lowest group, so it's 1, 2, 3. That is in what? That's an R configuration. That's the way a clock works. That's the right way. Okay, so I'm thinking it's 3, but I'm not too sure because this is it's an exam, so I'm gonna do the 4th one. Chlorine is top guy. It's gonna be 1, 2, 3, and 4. That's an S configuration, but then you're gonna have to do it again with put the hydrogen in the back. So really, it's gonna be like CH3. I know, it's a pain. So it's 1, 2, 3, and 4. That's our configuration, but then you're gonna have to reverse what you did. And so that's gonna be what? An S configuration. Yeah, it's just a repeat of what happened. So this for sure is S, and this is R. And so I'm going to say that is going to be 3. So answer choice C. Which one of these structures is S2-bromobutane? Well, we have to be chiral. Are we chiral over here? Let's see. Yep, that's chiral. Right here, it's chiral. That's chiral too, right? So what are we going to do? Right. Well, automatically you should be thinking, if it's chiral, I'm going to assign priority. Let's do it. We have priority number 1. The bromine has a higher atomic number. That's 1. I'd rather have a CH2 than a CH3. So I'm going to go 2, 3, and 4. My lowest priority group, sometimes it's not hydrogen, but in this case it's going to be hydrogen. My lowest priority group is in the back, and so we continue as normal. So 1, 2, 3. Okay, that's R. And 3 is incorrect because we're looking for S. Okay, what about number 2? We have 1, 2, 3, and 4. So it's 1, 2, 3. Well, that's wrong because your lowest priority group, in this case hydrogen, is on a wedge, and that's considered going in the front. And so all you have to do is just reverse what you did. So instead of having my arrowhead right there, I'm going to put my arrowhead on the other side, right? And so is going to go in a clockwise direction. That's the right way a clock works. That's going to be R, which is incorrect. So if you're in a rush, then for sure D is not correct. So maybe it's 1, but let's find out. Well, this is number 1. 1, 2, 3, and 4. So it's 1, 2, 3. But my hydrogen, or the lowest priority group, is on a wedge, and I want it to be on a hash. So I'm just going to reverse what I did. I'm going to do right here, and put my arrowhead on the other side, and that turns out to be a silly clock, right? So that's S configuration. It's very bad. So S configuration is counterclockwise, and that's pretty good. So I'm going to go with A, right? A is pretty good. Now, 6. Which of the following is true about S enantiomer? Right. So whenever you're doing enantiomers, it means that it has to be chiral. And if it's chiral, that means that it has to be bending light. So yeah, for sure, it's going to bend light. It's going to rotate, right? But, you can't tell that the light is going to be bending towards the right or to the left. Like, that's really random. It's really specific. You can't just say, oh, well, because it has this characteristic, for sure it's going to be bending at this degree to the left. Well, that doesn't make any sense. It's like, it's too specific, right? It's bad. It's way too specific. So anything that has to be dealing with, oh, S is always right or S is always left. No, sometimes it's left, sometimes it's right. So that's bad. A and B is bad. Terrible. Way too specific. So for C, it says a racemic form. A racemic means that you have a 50% S and then 50% R, right? Well, this could be true, right? But, you know, sometimes you're going to have a pure substance. Sometimes you have only 100% S. Sometimes you have 100% R. Sometimes you have 75% S, 75% R, and 25% S. Do you see? So, yeah, we have an S enantiomer, but we can also have like 1% R enantiomer. And so, I'm sorry. We can have an S enantiomer, but it could be 100% S enantiomer, right? There's an option to be pure, and this letter C is saying that it's always going to be 50-50. That's not true. So if you see that on the exam, that's not true. It could be a mixture of like 75-25, or it could be pure. So C is incorrect. Let's see. E, well, that's not true, because you can have your highest priority group on the right. You can have it on going upwards. You can have it going downwards. It doesn't have to be just the left, right? And so that's really too specific. It's too general. Or not general, but too specific. So E is incorrect. And yeah, an S is exactly the mirror image of an R, right? So just like conceptually, S is the mirror image of an R. They are counter opposites. And so D would have to be correct. And alkane, which can exhibit optical activity. So again, going back to this unit right there, that's technically optical activity. So optical activity is just a molecule's behavior towards light. And it's important for you to know that chiral molecules have behavior towards light, meaning that they exhibit optical activity. Therefore, an enantiomer also exhibits optical activity because an enantiomer is chiral. Okay? So whatever is achiral does not experience optical activity. So we're looking for a molecule over here that is chiral. Well, what about A? Neopentane just means that you have 5 carbons. So we have a carbon right here. That's 1, 2, 3, 4, say 5. So it's like an arm. So 1, 2, 3, 4, and 5. Sorry. Well, if we look at this center carbon, this carbon has 3 methyl groups. So 1, 2, 3. And since it has 3 of the same groups, it's going to be achiral. And achiral does not exhibit optical activity. It does not bend when exposed to light. It should say to light. So this is incorrect. Bad. What about isopentane? Isopentane is just, let's see, 1, 2, 3, 4, and we're gonna have like 5 right there. So you can see the kind of like iso group. You have a Y shape, kind of, and there's 5 carbons in total. So we have 1, 2, 3, 4, 5. That's isopentane. What's the problem here? Well, the problem here is that no matter where you look, you're gonna have repeating hydrogens. Over here, we have 2 bonds. Carbon wants 4 bonds, so we're going to do implied hydrogens. And that group right there, carbon has 2 hydrogens, so it cannot act as a stereocenter. This one has 3 hydrogens, right? And this is the same as this guy. So you have 3 of the same things. That's incorrect. That cannot be chiral. That's bad. That's achiral. And over here is going to have 3 hydrogens as well. And because we have repeating hydrogens, that's bad. So this is incorrect as well. Right? What about 3-methylpentane? Okay. 1, 2, 3, 4, 5. This is a 3-methyl. And that's an implied hydrogen. You can put your methyl group as a dash. by convention, by how I do it out of habit, I put it as a wedge, right? So is this good for me? Well, it's pretty bad. It's pretty bad. Why is it bad? Well, the reason why it's bad is because you have a methyl group. That's good. You have a hydrogen group. That's also good. That's different. But then we have a CH2. And whenever you're trying to figure out prioritization, you're going to have to go through each individual carbon. So that's a CH2. That's a CH2. So that's the same. Okay, let's go down the line. That's a CH3. And that's a CH3. And, well, nothing changed. And that's pretty bad. So we have the same group on each side. And that means we are achiral, because carbon technically has two of the same things on each side. So letter C is incorrect. That is incorrect. Right? But what about D? 3-methylhexane. 1, 2, 3, 4, 5, 6. Notice that it didn't say cyclohexane. So I just assumed we're doing a chain. So 1, 2, 3, 4, 5, 6. We have a 3-methyl. By convention, I put it on my wedge. And I do an implied hydrogen. Okay. Right. So methyl, hydrogen, that's good. We have a CH2. We have to go down the line to see prioritization. So we have CH2, CH2. That's not good. Okay, let's go down over here. We have a CH3 versus a CH2. And, you know, I'd rather have a CH2 than a CH3. And for sure, if I want to do prioritization, I would do number 1, 2, 3, and 4. And that would give me 1, 2, 3. That's going to give me an S conformation. Right. So this is S. And hey, you know, that's chiral. That's going to be D. If you want further proof, we can do letter choice E and show you why it's incorrect. So we have a 2,3 dimethylbutane. Butane is 4. 1, 2, 3, and 4. 1, 2, 3, 4. All right. And we have a 2,3. That's a methyl. That's an implied hydrogen. That's another methyl, implied hydrogen. So what's the problem here? Well, I just said that this is a methyl, and this is also a methyl. So technically that's a carbon with 3 hydrogens, and this is also a carbon with 3 hydrogens. And you can see the problem here. It's all the same thing for this guy. So that's the same. And so E is incorrect. That's actually achiral. So that's bad. Letter choice D would be correct. How many stereocenters are in question 8? Well, here's a trick. I know for sure it's not going to be here, because that's a hydrogen and that's another hydrogen. And so whenever you see crooks like this or this, it cannot be a chiral carbon. It cannot. Okay? That's bad. Alright. But what about junctions? What about if we have something sticking out right there? Is that a chiral carbon? Well, if we did it, let's see here. We have an implied hydrogen. Just, you know, always imply your hydrogens. To make it easier on myself, I just assume that your hydrogen is in the back, usually. Yeah, usually it works, right? Let's see. Well, we have a methyl group, which is different. Then we have a hydrogen. Then we have a CH2 and a CH2. Well, we have to go down the line. This CH2 is connected to an oxygen, so that's good. And this one has a CH3. Well, I'd rather have the oxygen right here and a CH2. So it's going to be like, let's see. I would say that this is like priority number 1. This is priority number 2, 3, and 4. Right? So we went down the line first. And I saw that, hey, well, I have an oxygen right there. So this CH2 is different from that CH2. Because this CH2 is connected to an oxygen, and that CH2 is connected to a CH3, which is different. So it's going to be a stereocenter. So for sure that's a stereocenter, right? Let's go over here, right? Do we have a chiral carbon? Well, let's see. We have an implied hydrogen over here. We have 1, 2, 3 bonds. I know that there's going to be a hidden bond right there. That's a hydrogen, right? And I'd rather have an oxygen right there. That's a CH2. That's a CH2. We have to continue down the line. That's a CH right there. This is a CH. Okay, we have to continue. That's a CH. That's a CH. We have to continue. This is a carbon. It's just a carbon. It has 1, 2, 3, 4 bonds. So that's a carbon compared to a CH3. So I'd rather have 1, 2, 3, and 4. So that technically is a chiral carbon right there. And they typically occur at junctions. So this is a chiral carbon. Or what about this guy? Because this is a junction technically. If you were to ignore this, this would not be chiral at all. But when you're introducing a substituent, which I call a junction, then, you know, sometimes it turns out to be chiral. So let's try this out. 1, 2, 3 bonds. That means we have an implied hydrogen right there. Okay. Well, we're going to try to do prioritization. It's a bad word. Terrible. So I'd rather have a CH right here than a CH2. That's 2. And then this is a methyl group right here. That's a CH3. So that's 3 and 4. So 1, 2, 3, 4. That's chiral. Completely different right there. And so I'm doing these little asterisks to show chirality. Right. Are we going to have a chiral center over here? Well, no, I'm not. Because we have 2 of the same groups right here. We have 1, 2, 3, 4 bonds. 1, 2, 3, 4 bonds. And, well, you have a you have a CH and a CH3. Or CH and a CH right there. So this carbon is going to have a hydrogen. And this carbon also has a hydrogen. And so you have 2 of the same groups attached to that carbon. That's not going to be chiral. But what if we go to the top? Well, we have an implied hydrogen. See how it's a junction. 1, 2, 3 bonds. That means that there's an implied hydrogen. This right here is not a junction because you have 4 bonds already. So that's an implied hydrogen right there. Well, let's go to the left and to the right. This is a CH3. I'm sorry. That's a CH and that's a CH as well. But this carbon is attached to an oxygen. And that's different from this guy, right? Okay, so we have something like that. And what else do we have? Well, we have a C. So this is just a single carbon. That's 1, 2, 3, 4. That's 4 bonds to that carbon, so it's just a C. Compared to 1, 2, 3, you're going to have an implied hydrogen right there. That's not an H. This is an H. So do I want a carbon or do I want a carbon with a hydrogen? Well, you know, I'd rather have the carbon. So this is going to be priority number 2, 3, and 4. So that is a chiral center. Okay, cool. They occur at junctions most of the time. Right? So would you agree that this is a potential chiral carbon? Well, yeah, I would say so because I know the answer, but, you know, it's a junction. I call them junctions because I'm pretentious, but that's just me, right? So 1, 2, 3, we have 3 bonds. We have an implied hydrogen right there. Okay, well, we have a CH. Do you agree that this is CH? We have 1, 2, 3 carbons, or 3 bonds. That means that there's an implied hydrogen. So that's a CH bond. And this is also a CH right here. So we're going to have to continue going down the line. So now we're here and we're here. That's a CH right here. And this is also a CH. So continue going down the line. We have this guy and this guy. So we have a CH with an oxygen attached compared to just a carbon? And do I want a carbon hetero atom, or do I just want a plain carbon? Well, I'd rather have a carbon with an oxygen compared to just a carbon. And so these are completely different molecules or completely different groups. So if I were to prioritize, I would say that this is group 1. So I'm just going to say left is group 1. This is group 2, 3, and 4. And see, there are 4 different groups. When I say 1, I mean going like to the left. And those are 4 different groups, so for sure that's going to be a chiral center. Alright, so we have 1, 2, 3, 4, 5. 3. So we're not done yet. We have to go. Continue. Is this a chiral center? No, because you have hydrogen and hydrogen right there. So that's pretty bad. Same for that guy. But what about this? Because that's a junction, technically. Okay. Well, let's see. We have 1, 2, 3 bonds. So we have an implied hydrogen right there. Okay. Right. So how am I going to prioritize for this carbon? Well, I'd rather have, well, first of all, do I want a H2 or do I want an oxygen? Yeah, I want an oxygen, okay? So I want to go number 1 right there. That's number 1. Now we have to kind of like do a tiebreaker because you have a CH2 and a CH2, right? So a CH2 and a CH2, they're the same, so we're going to have to go down the line again as a tiebreaker. This is a oxygen versus a CH2. What am I going to prefer? An oxygen or a carbon? I'm going to prefer the oxygen. So I'm going to say that this is priority number 2. This is 3, and that's 4. Notice how there are 4 different things, right? 4 different priority groups. We're going to say that this is a chiral center. And before I forget, sorry, we forgot to check a junction. So junctions are typically like a Y shape. Okay, so I kind of like forgot that this is like a Y shape. And so most likely it's going to be a chiral carbon. So let's make sure, because I don't want to steer you wrong, I guess. So that's an implied hydrogen, because this is 1, 2, 3 bonds. We want 4 bonds right there. That's going to be a implied hydrogen, right? So now we have a CH2 versus a what? A CH. And so I'd rather have the CH than the CH2. So that's going to be like priority number 1, right? Then we have a C. Wait, hold on, sorry. I'm sorry. This is a CH versus a CH. So we're going to have to go down the line again. So that's CH2 versus a what? 1, 2, 3. That's a CH. So this guy versus that guy. So that's a CH2 versus a CH. I'd rather have him. So that's 1, 2. Right? And let's see. We have like CH2 right there. That's carbon 3. And that would be 4. So that's going to be a chiral carbon as well. So yeah. If you wanted more help for that one, because I know even I think it's kind of weird, but if you want to think about it, this is going to be priority number 1. But now we have to do between this guy and that guy, okay? So let's see. Right here, we have an oxygen, and over here we have a carbon. And you know what? I'm sorry. I apologize because I just double-checked my work right now. I apologize because, I'm learning the material as well. But this is not priority number 1 because right here, so for sure this is a CH and for sure that's a CH. So we're going to have to go down the line again, right? Okay, so now we're over here and we're over here. That's a carbon attached to an oxygen, and that's a carbon with a hydrogen. I'd rather have the oxygen first. And so I'm going to say that this is 1. This has to be what? Well, we don't know if this is 2 or 3. Well, now we're dealing with this guy or that guy. What do I want a CH2 or do I want a CH3? Or I'm sorry, a CH. Well, I'd rather have the carbon with one hydrogen. If you can't see the hydrogen, it has 1, 2, 3 bonds, so we want a hydrogen right there. Okay, so I'd rather have the carbon with a hydrogen compared to a carbon with 2 hydrogens. So it's going to be 2 and 3. And that's going to be 4. So as you can see, that's a stereocenter as well. Okay, they occur at junctions. And over here, well, you have a double bond, or not a double bond, but 2 bonds, and you have a substituent. And if you look at it, that's a Y shape, so it's like a junction. Okay, so 1, 2, 3 bonds, we have an implied hydrogen going in the back. Okay, well, for sure, this is going to be priority number 1 because there's an oxygen directly attached to my potential chiral center. This is going to be number 1. Now we're going to go down the line. We have CH2, CH2. Okay, we have to do a tiebreaker. We have to go down the line again. So that's a carbon attached to an oxygen, and that's carbon double attached to oxygen. So whenever you have a carbonyl is just oxygen double bonded to a carbon. You can consider this as equal to a carbon with 2 oxygens. So it's like, it's more, it's higher priority. So I'm not saying that you have 2 oxygens, I'm just saying that you should consider it as 2 oxygens, right? And so I'd rather have a double bonded oxygen than just a single bond oxygen to this carbon, right? And so this is going to be priority number 2, 3, and 4, right? So that's a chiral carbon right there. And, you know, that problem took a lot longer than I anticipated. But hey, we have 1, 2, 3, 4, 5, 6, 7, 8. 8 chiral carbons. And now you know how to do chiral carbons for weird Mevacor registered trademark, right? So it's 8. 8. They occur at junctions, most likely. All right, so which one is a Miso compound? Which one is a Miso compound? Again, to be a Miso compound, you have to have a chiral molecule at first, okay? So when I see Miso, I'm going to be saying to myself, well, you know, you should, look for a molecule that is chiral, or at least achiral, because if you find something that is achiral, then it cannot be Miso. So we have a hydrogen and another hydrogen, and so that's not chiral at all. So it cannot be 4, because Miso makes a chiral molecule become achiral, okay? So now technically everything is chiral. You have alcohol, oxygen, or hydrogen, methyl, carbon. Okay, so that's okay. That's good. This is chiral. That's chiral. But now we have to find our symmetry. Our symmetry. Well, is 3 and 5 symmetrical? No, because they have completely different things, right? They have different things in different angles. So there's no plane of symmetry over here. There's no plane of symmetry over there or there. So 3 is incorrect. And the same thing is true for this guy. So no plane of symmetry there or there or there. So that's bad. So we eliminated answer choice 3, 4, and 5. Right? So it's either A or B. Well, let's see. Let's do number 1. All right? Let's do number 1. Okay, so this is chiral, and I'm trying to look for a plane of symmetry. Well, here's a little trick that you need to learn. First of all, this is the chiral center, and that's a chiral center, and this is not a chiral center. But that doesn't matter, okay? It's just like a red herring, just like a trick to just kind of throw you off the answer. So don't fall for that. Just ignore this carbon. Okay. So what I want to do is I want to get my alcohols or whatever on the same side. So my alcohol or methyl group, whichever you prefer, is going downwards. This is going upwards. Well, no matter what, I want them to go downwards. Okay? So I'm going to rewrite it as them going downwards. And technically that carbon with 2 H's right there, that's just a peak. Right, so it's just a peak right there. Okay, let's do it over here. That's a methyl group. It's alcohol. Okay, and I want my alcohol to be going downwards, so we're gonna have this peak right here. This is a hydrogen. That's a hydrogen. And now notice, here's something very important. You gotta pay attention to this, write it down. Whenever you twist something, all we're doing is twisting this part. This is a single bond, we can twist, right? So we're twisting over here. Let's do it in green or blue, or no, green. So whenever we're twisting, whatever was a wedge becomes a hash. So my alcohol was a wedge, it's gonna be a hash. And so my methyl group which was a wedge, which was a hash becomes a wedge. And whatever was a wedge becomes a hash. Right? And notice something. We have a plane of symmetry. Isn't that cool? And so you were chiral, but because we only twisted it, we have a plane of symmetry. And so that is a Miso compound. So answer choice A would be correct. But what about B? Well, if you twisted it so that hydrogen is going upwards with hydrogen, well, this wedge becomes a hash, and this hash becomes a wedge. And so you're going to have a wedge alcohol compared to a hash alcohol. And so that is not symmetrical. You cannot compare wedge and hash, right? So hash and wedge, they're different. They're not symmetrical. That would still be chiral. And so we're looking for Miso. A would be correct. And, just remember that trick, right? Hopefully question 11 is a little bit easier for you to see. If you're a person who likes to feel things like in their hands when they're doing chemistry, you could do like a model kit. But for me, I just like looking at the pictures. What I'm noticing is that picture A and picture B, there's the same thing. Why? Well, if I were to get if I were to pinch this part right here and flip it over, right? Well, this point that I pinched would be over here, right? And then this guy would be flipped to that part, and this H would be flipped to that part. And see that H, which was down, is going to be up. This was up, that's going to be down. This was down, that's going to be up. This was up, that's going to be down. And so all you did was you literally just took it, flipped the tray, and you're going to have the same compound. So if you take a plate and you flip it over, is it the same plate? Yeah, it's going to be the same plate, right? You're not going to have a golden plate when you flip it over. It's going to be the same compound. So, yeah. So which statement is true about 1,3-dimethyl-cyclobutane? Okay, well, you obviously have to draw that out. It's a cyclobutane, so you're going to have a picture. 1, 2, 3, 4, 5, and 6. So we have 1,3-dimethyl-cyclobutane. By convention, I just put, butane on a wedge. That's 1, 2, 3. Bu just means butane. I'm just lazy. Right there, that's a hydrogen. Right. Oh, I'm sorry, not a butane. I thought we were doing hexane, I'm sorry. So butane means that it's 4. So that's just a square. And we have carbon 1. We can have like a methyl group right there. 1, 2, 3. 1, 2, 3, it doesn't matter. Right, I'm sorry. So that's going to be a methyl group. These are implied hydrogens. Okay. So only one form of the compound is possible. Well, that's a lie, for real. That's a lie, because you can also do this. Sorry. Right there, and so notice that this is side A. I'm not flipping it. This is also side A, right? And notice that I kind of like, that's kind of like a constitutional isomer because I didn't change my position. I'm just switching the places. And so that is a different form of the compound. So answer choice A is incorrect. What about B? Well, B, you're doing a diastereomer. So diastereomer is when one is upwards and the other is downwards. So for instance, we have a methyl group that's going upwards. Then we're going to have a methyl group going downwards. And so we have a methyl group going upwards, that's a wedge. And then we have a methyl group going downwards, that's a hash. That's a diastereomer. Well, what if we did this? What if we did the methyl group going downwards over here, and then a methyl group going upwards over here? And this is side A, and this is side A, so I'm not flipping it. Well, that's a different form, right? So that's technically a different form of a diastereomer. So, yeah, answer choice B would be correct. Moving on. The molecules below are what? What are they? Are they constitutional, enantiomers, diastereomers, or identical? Well, first off, always check if they're chiral first. So hydrogen, fluorine, methyl, nitrogen, fluorine, methyl. So that one's chiral, and that one is also chiral, right? Now let's assign priority. So fluorine is going to have a high priority. That's that. Do I want a CH3 or do I want a carbon that has 4 things attached to it? Well, I'd rather have a carbon that has 4 things attached to it. So I'm going to go down 2. This is going to be 3, and that's 4. That's 1, 2, 3. But notice that hydrogen is on a wedge, and I want hydrogen, or whatever is my lowest priority group, to be on a hash. And so I'm going to have to reverse what I did. So technically, that's S. Okay, so this is S right there. What about this one? Well, fluorine is the higher priority. Nitrogen is second. That's 2. I'd rather have a carbon with three things attached to it than a carbon with 3 hydrogens. So that's a carbon, right? So that's going to be 2. I'm sorry, 3. That's 4. So 1, 2, 3, right there. But look, over here, methyl is my lowest priority group. It's number 4. It's also on a wedge. We didn't have a hydrogen that time, but we had a methyl group. And I don't care if it's hydrogen, I just care about my lowest priority group. And so yeah, we're going 1, 2, 3, but I'm going to have to reverse it. Instead of going that way, I'm going to have to go this way. So that's what? That's an A, I believe, counterclockwise right there. So that is counterclockwise. So that's SS, right? Now we're going to do the right hand, or the right-sided. This is priority number 1, 2, 3, and 4. So that's 1, 2, 3. But hydrogen, or the lowest priority group, is on a wedge. So we're going to have to reverse it. That's going to be what? R. And over here, we have priority number 1, 2. I'd rather have a carbon with 3 things attached to it compared to a CH3. So it's going to be 2, 3. Oh, I'm sorry, not 2, but rather 3 and 4. So again, methyl group is on the 4th carbon, or on the 4th. I'm sorry, methyl group is a low priority, and it's on a wedge. So you're going to have 1, 2, 3. But you're going to have to reverse what you did. So that is what? That is an S. So over here we have SS for the left side, and on the right side we have RS. So notice that this S stayed the same, but this S right here became an R, and whenever something changes like that, you're gonna have a diastereomer. So it would be C, a diastereomer. What about this one? Well, okay, first of all, I noticed that I have 2 hydrogens to this carbon on both of them. And so that carbon is not chiral, so we're going to ignore it. We're going to ignore this section right there. However, don't throw it away in the garbage yet, because you have two possible stereocenters. So one stereocenter failed, but you have a backup. Is this a stereocenter? Well, you have a hydrogen, a bromine, and a methyl group, and then you have a carbon right there. So that's completely different. So that is a chiral center, and it's the same thing over here. Now we're going to assign priority. I'd rather have a bromine because it has a higher atomic number. And do I want a carbon with 3 things attached to it, or do I want a carbon with hydrogen? Do I want a carbon with a hydrogen, or do I want a carbon with 3 hydrogens? Well, I'd rather have the carbon with a hydrogen compared to a carbon with 3 hydrogens. So I'm going to say 1, 2, 3, and 4. So it's 1, 2, 3. But notice that this hydrogen, which is my lowest priority group in this case, is on a wedge. And so I'm going to put my arrowhead on the opposite side. And what is that? Oh, that's R. Okay, so that's R. Alright, now let's do this in green. This is priority number 1. This is priority number 2, 3, and 4. So it's like this, 1, 2, 3. But hydrogen, or the lowest priority group, is on a wedge. So my lowest priority group is on the wedge. I'm going to have to reverse what I did. That's going to be, what? An S configuration. So now you're comparing apples to bananas. We have R compared to just an S. And what is that? Well, it turns out to be diastereomer. Not diastereomer, but rather enantiomer. So this is correct, enantiomer. Not diastereomers. Diastereomers only occur with 2 or more chiral centers. So we're going to call that chiral centers. Notice we're only working with 1 chiral center, and so enantiomer looks pretty good for us. R became S, that's enantiomer, and that was a pretty fun problem. Not too bad. The reason why this is not identical is because if it were identical, you would have a hydrogen right here and a hydrogen right there. And so that is not identical. That is not identical. Well, is it a diastereomer? A diastereomer is cis and trans. Well, this is up, so that's cis. And this is what? Down, which is cis as well. So we're not experiencing a diastereomer relationship. This doesn't matter, right? Because cis and trans only relates to like 2 of the same atoms. So hydrogen is the same as another hydrogen, right? I hope you agree with me on that. And so these 2 same atoms are both going upwards, so that's cis. On the second picture, they're both going downwards, which is also cis, so that's bad. That's not a diastereomer. Okay. Well, what about constitutional isomers? Well, technically it's a constitutional isomer, but it's a subsection of constitutional isomer. It's actually an enantiomer. So how did I get enantiomer? If you're not comfortable with this picture, you can draw out a different picture. So we're working with a triangle. You agree with me that hydrogen is going up, right? Okay, if hydrogen is going upwards, we're going to say that it's a wedge. And whatever going downwards is going to be a methyl group. Over here, hydrogen is also going upwards. And what's going downwards is my fluorine group. So let's draw another triangle. Over here, what's going upwards is my methyl group. What's going downwards is my hydrogen group. On this part, what's going upwards is my fluorine group, and what's going downwards is my hydrogen group. So now let's assign priority. Let's do for this stereocenter right here. This is priority number 1. Now, would I rather have a carbon that's attached to 4 things, or do I want a carbon that has 2 hydrogens? Well, if you can't see it, that's a hydrogen right there. So I'd rather have a carbon that has 4 bonds compared to a carbon that has 2 hydrogens. So that's going to be priority number 2. Now this is 3, and that's a methyl group, which is a CH3. CH2 is better than a CH3. We're going to say that's 4. So 1, 2, 3. But notice that my my lowest priority group, in this case methyl, which is number 4, is on a wedge. So whatever I do, I have to reverse it. So it's going to be what? It's going to be clockwise. So that's R. Alright. What about this stereocenter? Alright. I'd rather have a carbon that has a fluorine right here. So that's going to be priority number 1. And do I want a CH2 or do I want a methyl? Well, I'd rather have a CH2. So it's going to be carbon 2 or priority 2, priority 3, priority 4. All right. So it's going to go 1, 2, 3. But our lowest priority group, which is hydrogen, is on a wedge. So what I do, I'm going to have to reverse it. That's going to be S. So we have R and S. Right? We're going to go over here. We have fluorine, which is priority number 1. Again, I'd rather have this guy, 2, 3, and 4. So that's 1, 2, 3. Our lowest priority group is on the bottom. It's on the bottom right there. And you know, I apologize. I said that this was a methyl. This is actually hydrogen. I'm sorry. Continuing, we have 1, 2, 3, and that's going to be S, because our lowest priority group, which is hydrogen, is on a hash. So it's going to be S configuration. Alright, what about the top one? Well, the top one, we have, well, do I want a carbon with a fluorine? Yeah, for sure, I'm going to put that as 1. And do I want a CH2 or do I want a CH3? I want the CH2. Right there, that's going to be 3. That's 4. So that's 1, 2, 3. Right? Hydrogen is in the back. So it's going to be R. So now we're comparing RS compared to SR. And so this R became S, and this S became R. And whenever you have that relationship, it may be Miso, it may be Enantiomer, right? So you're kind of having like a toss-up. Well, is it going to be Miso? Is it? No, it's not going to be Miso. Why is that? Because you don't have a plane of symmetry. Yeah, that's right. Because they have a fluorine and a methyl. To be a plane of symmetry, you have to have like the same substituents, right? So fluorine is different from a methyl group, so it's not symmetrical. Same thing for this guy. So that's not Miso. It's not Miso, so it has to be an enantiomer. So it's going to be B. Oh yeah, pretty cool. So which one represents an enantiomer? Well, let's see. To be an enantiomer, you're going to have, you know, like SSRR, right? So it's not good if you're achiral. This is achiral. That's hydrogen and hydrogen. So that's wrong. Is there any repeats over here? Let's see. No. So these are all chiral, right? And we're looking for pairs, by the way. So I wanted like SS and I wanted like RR, right? Well, if I only have S and I have that, is that enantiomers? No. So because this one only has one chiral center, I can't do enantiomers for pairs. Okay? Okay. Well, here's the trick. If you have the same atom or molecule on the same side, then most likely you're going to have a repeat. Meaning that if I have S on here, I'm going to expect an S over here. If I have an R over here, I'm going to expect an R over there. So that's alcohol right there, and they're on the same side, wedge. Over here, well, you have a hydrogen right there and a hydrogen right there, but they're on different sides. They're on opposite sides. And, well, I'm expecting like a SR or like RS, something different. So no repeats. And so we can say that 4 is wrong. So it has to be 2 and 3. That's if you're in a rush, right? But let's prove it. And it's going to take us like 5 hours the way I do it. So it's 1 2, 3, and 4, right? That's going to be what? That's going to be S. S right there. S. Over here on green, we will have 1, 2, 3, and 4. Hopefully you can do prioritization now. If you don't, then check out my other video. It's like 2 hours long, right? So that is 1, 2, 3. 1, 2, 3. And hydrogen is in the front. It's on a wedge. My lowest priority group is on a wedge, so it's going to go this way. So that's also S. It's also S. Alright, so as you can see, we had a repeat, S and S. Alright, is this true for the other one? We'll see. This is priority number 1, 2, 3, and 4. That's 1, 2, 3. Well, our lowest priority group is on a wedge, so we're going to have to reverse it. So that becomes R. That's R. Right. What about this one? 1, 2, 3, and 4. So that's 1, 2, 3. My lowest priority group is on a hash, so that's good. We're expecting an R conformation. So that's also R. So we have SS, it became RR. That's going to be an enantiomer. And so for sure it's going to be 2 and 3. That's a quick way to do it. Over here, we have 2R and 3R. Well, first of all, this means that I have to be chiral, right? Both of my stereocenters have to be chiral to get a letter. Well, this one is not chiral. It has a hydrogen and another hydrogen. So that's bad. You can't have one chiral center. Both of them, in this case, has to be chiral. That's wrong. And we want to repeat, right? We want to repeat. So RR. All right. Well, the trick that I just showed you gives us repeats. And so this does not have two of the same groups. That does not have two of the same groups. So that sucks. You could throw it away. You could burn it, I guess, or nuke it, right? So this is, it's the same thing as you see it on above. So it's going to be like answer choice C. It's the exact same thing. And, I'm not going to waste time doing it. But that would be 2R, 3R. So we have an R, that would be S, and S. As you can see, repeats because of this, and it repeats because of that. So we're looking for 2R. This is going to be 2R. It's going to be 3, 3. So which one does not possess a plane of symmetry? Well, for sure, this one has a plane of symmetry. That's the same as that guy, and that's the same as that guy. So 1 is incorrect, A is wrong, B is wrong, E is wrong, right? This one is not correct. This one is correct 3 because it does not possess a plane of symmetry. You have a hydrogen going upwards, you have a hydrogen going downwards, so that's a wedge, that's a hash. You have a bromine going downwards, that's a hash. And then you have a bromine going upwards, that's a wedge. And so this is not a plane of symmetry. 3 for sure is correct. This one, again, hash is different from a wedge, so that's not symmetrical, so 4 is correct, okay? But what about 2? Well, again, listen to me. To be symmetrical, you have to have the same atoms on both sides, right? So that's a chlorine, that's a hydrogen, that's a hydrogen. Maybe we should have a chlorine? Oh wait, that's a methyl group. Right, that's a methyl group, sorry. That's a methyl group, so that's not going to work out for me because, well, it's not going to have a plane of symmetry. Well, yeah, I get it, but the reason why it's not correct is because to be considered for symmetry in the first place, you have to have the same atoms. This has different atoms, and so it's not even considered for symmetry because it has different atoms. So if you have different atoms, don't even consider it for symmetry. So yeah, it's not symmetrical, but it wouldn't be symmetrical in the first place because it has different atoms. So 2 is wrong. It has to be D. I'm sorry, D, 3 and 4. Yeah. So there we go. Which one is a Miso compound? Great. Which one is a Miso compound? So it's most likely not A or E because we have most of our answer choice as B, C, or D. But let's prove it. So we have butane. That's 1, 2, 3, 4. 1, 2, 3, 4. We have 2, 3. bromo. By convention, I just put it on wedge. Okay, so a Miso compound means that they're gonna be symmetrical. So this is chiral, that's chiral. You know, can I make this into a symmetrical compound? Well, I could twist this. I could twist it and get this. Always have something on orientation. Of course, I explained this a lot in the previous video. But whatever was a wedge becomes a hash. And whatever was a hash becomes a wedge. And so a bromine on a wedge is different from a bromine on a hash. And so that's not symmetrical. It's not symmetrical, therefore it cannot be Miso. So answer choice A is incorrect. What about B? Or, you know, what about E? Or, yeah, what about E? Well, for E, we have hexane. It's not a shape, it's just hexane. So 1, 2, 3, 4, 5, 6. Right? And then we want something on this one. That's bromo. And I'm pretty lazy, so I'm not going to draw hydrogens. 1, 2, 3, 4. That's a bromo. Are we going to be symmetrical? Well, or that's not intuitive, I guess. You know, if we got rid of this guy, we could be symmetrical. We could. But this extra carbon kind of throws me off. It makes us asymmetrical. So because of that extra tail, we're not going to be symmetrical. We're not going to be even. And so answer choice E is incorrect because we have an extra carbon. So it's either B, C, or D. Right, so let's draw a pentane. 1, 2, 3, 4, 5. Then we have something on 2. We have something on 4. Right? Okay. So if I want this to be Miso, that's going to be what? That's going to be Miso. Because we have a wedge bromo and a wedge bromo. Okay. So that's cool. But what is it? Okay. If we're going to assign priority, we're going to say that this is priority number 1. Do I want a CH2 or do I want a CH3? I want a CH2. So that's 2, 3, 4. That's 1, 2, 3. Right? Lowest priority group is on the back. So that's going to be R, confirmation. That's going to be 1, 2, 3, and 4. So that's 1, 2, 3. So it's going to be R and S configuration. So right there, we'll see R and S, so that's going to be S. And so this problem also shows you how to name compounds. We have 2R, 4S. R comes before S in the alphabet, and then 2, 4 dibromopentane. So for this one, I guess you could just draw the pentane like I did and then try to make it Miso. And in this way, you would have a Miso compound. So that would be a 2R and 3S. That's 1, 2, 3, 4, right? So it would be D, 2R, 4S, 2, 4 dibromopentane. Now what about 20? 1 and 2 are what? What are they? Well, fluorine stayed the same. This guy stayed the same. Kind of. Well, you have 1, 2, 3, 4. So it's like a isobutyl, right? Or I guess you could say T-butyl. Yeah, T-butyl. And what happened? Well, all you did was you turned this guy over there. Well, first of all, it's diastereomer. How do I know that? Well, diastereomers, they typically occur at double bonds. So over here, we have this guy going downwards, we have this guy going upwards. And since you have up and down, there's going to be cis and trans. If that doesn't make sense to you, this peak is going downwards, so my hydrogen is going to go downwards. And my hydrogen right here is going to go upwards since this peak is going upwards. And of course, you can make them wedges or hashes. Over here, our peak is going downwards. So my hydrogen is going downwards. And over here, my peak is going downwards. So this was this is going to be H, right? So that's also going to be downwards. So this one's going up, this one's going down, this is going down, and this is also going down. And so this up became a down, and this down stayed a down, right? So we have a cis and trans relationship. So this is cis, trans, and that means that this becomes a diastereomer. And that is basically as simple as that, right? They're not enantiomers. I'm pretty tired, so I'm not going to actually write it out for you, but it would be diastereomer because of that cis-trans relationship between the double bond and the implied hydrogens. If you see something like that, most likely be on the safe side and draw out your hydrogens or whatever and see if it's a cis-trans relationship. If nothing else changed, you just kind of rotated this, right? So there'd be diastereomers. I hope you do well on your exam. Thank you for watching. I messed up a lot in this video, but it's great. I'm sick. My voice is cracking. That's awesome. My lips are chapped. But, I do it for you guys. I love you. I hope you do well on your exam. Stay studying and, have a great day.